This session is for explaining the answers of tutorial of module 3. Before watching this video, all are required to download the answer key of module 3 tutorial, which is already uploaded in the Moodle portal. So let us move to question number 4. Here a system is represented by x dot equal to ax, and its response for two different initial conditions are given. That is, x of t is equal to 2 e raised to minus 4t e raised to minus 4t when the initial condition is 2 1. For another initial condition x0 equal to 4 1, the response is given by 4 e raised to minus 2t e raised to minus 2t. It is asked to find the state transition matrix as well as matrix A. So we all know that x of t equals Laplace inverse of Si minus A inverse x of 0. We just substitute in this equation the two different conditions. For any system, Laplace inverse of Si minus A inverse will be the same, because it depends just only on capital A, which is a system matrix. So let us put the two conditions, that is 2 e raised to minus 4t e raised to minus 4t equals, assuming that Laplace inverse of Si minus A inverse is given by A, B, C, D matrices 2 1, 4 e raised to minus 2t e raised to minus 2t equals A, B, C, D 4 1. So we have two equations, that is 2a plus b is equal to 2 e raised to minus 4t, 2c plus d equal to e raised to minus 4t. We have 4a plus b is equal to 4 e raised to minus 2t, and 4c plus d is equal to e raised to minus 2t. This results in two different equations for a and b each. Also we have two equations for c and d each. Solving this, we get a equal to 2 e raised to minus 2t minus e raised to minus 4t, b equals 4 e raised to minus 4t minus 4 e raised to minus 2t. Similarly, c is equal to half e raised to minus 2t minus half e raised to minus 4t, and d equals 2 e raised to minus 4t minus e raised to minus 2t. We have e raised to minus 2t. So this is the solution for a, b, c and d. This can be substituted in the equation Laplace inverse of Si minus A inverse equal to 2 e raised to minus 2t minus e raised to minus 4t, then 4 e raised to minus 4t minus 4 e raised to minus 2t, half e raised to minus 2t minus half e raised to minus 4t, 2 e raised to minus 4t minus e raised to minus 2t. So we can find Si minus A inverse, that is Laplace transform of this matrix. So this results in 2 by s plus 2 minus 1 by s plus 4, half by s plus 2 minus half by s plus 4 4 by s plus 4 minus 4 by s plus 2, 2 by s plus 4 minus 1 by s plus 2. On simplification, we get s plus 6 minus 8, 1 s by s plus 2 into s plus 4. So basically this is adjoint of Si minus A by determinant of Si minus A, because it is Si minus A inverse. So the numerator matrix will be nothing but adjoint of Si minus A. This results in Si minus A as S8 minus 1 S plus 6, which results in capital A is equal to 0, minus 8, 1, minus 6. Now coming to the next problem, that is question number 5. We have already discussed Cayley-Hamilton theorem in the lecture notes, but the problem that was included had distinct eigenvalues. So I thought of including a case when we have repeated eigenvalues. So the question is, find the state transition matrix when capital A equals 0, 1, minus 1, minus 2. So basically, based on Cayley-Hamilton theorem, we start with the eigenvalues. So for which we need to find lambda I minus A, we have lambda minus 1, 1, lambda plus 2. This results in determinant lambda I minus A equal to 0, for which lambda 1 equal to minus 1 and lambda 2 equal to minus 1. Both are same. So this is why this is called repeated eigenvalues. So we have seen that according to Cayley-Hamilton theorem, every matrix will satisfy its characteristic equation. So for which we write f of lambda equal to e raised to lambda t, that is alpha 0 plus alpha 1 into lambda, and substituting this as lambda equal to minus 1, we have e raised to minus t is equal to alpha 0 minus alpha 1. But if you substitute the second eigenvalue, we will get the same equation. So to avoid repetition and also avoiding getting similar equations, what we do is we find df lambda by d lambda. So this will be nothing but t e raised to lambda t will be equal to alpha 1, taking the derivative on both sides. Then substitute alpha equal to minus 1. So this is implies t e raised to minus t equal to alpha 1. So we can solve for alpha 0 also. Alpha 0 will be e raised to minus t plus t e raised to minus t. So in this case, we can use f of a. To find f of a, alpha 0 I plus alpha 1 a, because that is the same as f of lambda, because the matrix satisfies its equation. So any a lambda can be replaced by capital A. So we have e raised to at as e raised to minus t into 1 plus t, t e raised to minus t, minus t e raised to minus t, e raised to minus t minus t e raised to minus t. So this problem has some significance because it deals with repeated eigenvalues. So you should keep in mind that when we have repeated eigenvalues, first we consider f of lambda and then we consider d by d lambda of f of lambda. Now we move on to question number 7. This question asks us to find the CCF of a given state model. We had discussed in detail how we can find the CCF given any state model. Basically, there are two methods. One can find the transfer function first from the given state model. The transfer function can be converted into controllable canonical form. Else we can use similarity transformation. So, this problem is basically using similarity transformation. So, we have seen that any state model x dot equal to ax plus bu and y equal to cx plus du can be converted to CCF provided we have a linear transformation which is given by x is equal to px bar. So, we can see that x bar dot will be P inverse AP into x bar plus P inverse B into U. Similarly, y is equal to Cp x bar plus du. So, how to find P? P is nothing but S into M. So, I had mentioned that S is nothing but a matrix which is obtained by arranging B and AB. As far as this problem is concerned, B is 2, 1 and A is minus 1, 1, 0, 2. So, we can form S by arranging B first. B is 2, 1. Then we arrange the column which is obtained by the product of A and B. And this can be obtained as minus 1, 2. It can be noted that the size of A and size of B will be the same. Now, we can find capital M. How to find capital M? For which we need to find lambda I minus A equal to 0. It results in lambda square minus 1 lambda minus 2 equal to 0. So, this can be compared to the standard form of lambda square minus plus A1 lambda plus A0 equal to 0. So, these coefficients basically gives A0 and A1. This also is explained in the lecture handouts. So, we have P is equal to, M is equal to A1, 1, 1, 0. So, that results in minus 1, 1, 1, 0. If we have more matrices, the size of the matrix will keep on increasing. So, we have P is equal to S into M, that results in minus 3, 2, 1, 1. Then we get x bar dot is equal to P inverse AP x bar plus P inverse B into U, y equal to Cp x bar plus du. So, that gives x bar dot is equal to 0, 1, 2, 1 x bar plus 0, 1 into U, y equal to minus 1, 4 x bar. So, we can see that this matrix is in the controllable canonical form. The controllable canonical form is 0, 1, 0, 0, 0, 1, minus A, minus B, minus C. So, if it is a 2 by 2 matrix, we will have 0, 1, minus A, minus B. It can be either positive or negative. and this matrix will be 0, 0, 1. So, if you have only 2 by 2 second order system, it will be 0, 1. So, that is CCF. Next is conversion to question number 8, conversion to diagonal canonical form. So, in this I have told the matrix of transformation is x is equal to Tx bar. So, if you have a linear transformation like this, then T inverse AT will give you a diagonal form. So, I will just explain how to find capital T. Capital T is obtained by arranging eigenvectors one after the other. So, first we need to find lambda I minus A and its eigenvalues, that is lambda minus 1 0, 0 lambda minus 1, 6 11 lambda plus 6. The eigenvalues are lambda 1 equal to minus 1, lambda 2 equal to minus 2, lambda 3 equal to minus 3. To find eigenvector, we use an equation lambda I minus A into m 1 equal to 0, where m1 is the eigenvector. It should be noted that eigenvector is a non-zero vector, which means all the elements of m1 cannot be 0. But if you look at this equation, you can see that we can have a solution with m1, entire m1 equal to 0. That should not be taken for eigenvector. That is the most significant step of this solution. So, we substitute the various values of lambda I in this equation. So, let us assume that we are going to find the eigenvector corresponding to lambda I is equal to minus 1. So, that results in minus 1. Substitute in this equation lambda is equal to minus 1, because we are going to find the eigenvector corresponding to the first eigenvalue. So, minus 1, 0, 0 minus 1, 6, 11, 5 into m1 can be written as a vector whose elements are m11, m21 and m31. These 1, 2, 3 correspond to the various rows of matrix m1 equal to 0, 0, 0. This results in minus m11 minus m21 equal to 0, minus m21 minus m31 equal to 0, and 6 m11 plus 11 m21 plus 5 m31 equal to 0. We can see that the solution for these three equations can be m11 equal to 0, m21 equal to 0 and m31 equal to 0, but we should not take that. So, in order to avoid such conditions, what we do is we write one of the variables as a standard variable and write other variables in terms of that. That is something like m21 is equal to minus m11, m31 is equal to minus m21, and let m11 equal to 1. This results in m21 equal to minus 1 and m31 is equal to 1. It is not necessary that you should choose m11 as 1 alone, always. It can be any scaled value. So, eigenvector in this case would be m11, m21, m31, that can be 1, minus 1, 1. It can be any scaled versions. It can be like the whole matrix can be multiplied by minus 1. Another eigenvector for lambda I equal to minus 1 can be minus 1, 1, minus 1. That is this matrix when multiplied by minus 1. I can multiply this matrix by 2 and I can have an eigenvector corresponding to lambda I equal to 2 as, lambda I equal to minus 1 as 2 minus 2, 2. Any scaled version of this matrix can be an eigenvector. Then we arrange the matrix, the eigenvectors of all the 3 eigenvalues one after the other, that is m1, m2 and m3, where m1 is the eigenvector corresponding to lambda I equal to minus 1. This is the eigenvector corresponding to lambda I equal to minus 2, and this is the eigenvector corresponding to lambda I equal to minus 3. Once we get T, we can easily find the diagonal matrix. Refer to the handouts. Thank you.